Hi students, according to the kinetic theory, a gas consists of a Godzillion number of gas particles in random motion. And when these particles collide with the walls of the container, they exert pressure forces on the walls of the container. And that's where the pressure of a gas comes from. Obviously, the pressure of a gas is related to the speed of the gas particles. So can we derive a formula for the pressure of a gas based on the molecular motion? That sounds like a very daunting task because there are Godzillion number of gas particles and they are all going at different direction and different speeds. So what we can do is to start with a simpler model first. So let's assume that all the gas particles move only in the x direction and they all move at the same speed v. Let's just focus on this gas particle and ask how often does it collide with this wall. So this guy is going to do bang, 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 bang. If it's traveling at speed v and if this distance is l, then the time interval between consecutive collisions should be 2l divided by v, because after each collision it has to travel l plus l before it makes the next collision. Because it's a elastic collision, after each collision the gas particle will rebound with the same speed. So the momentum before the collision is mv and the momentum after the collision is mv in the opposite direction. So the change in momentum for each collision should be 2mv. M is the mass of each gas particle. From Newton's second law, we can figure out that this gas particle, on average, would be exerting this amount of force on this wall. And it works out to be mv square over L. But this is not the only gas particle banging against this wall. There are, let's say, n number of gas particles. So the total force should be n times of mv square over L. So the pressure on this wall would just be the force exerted on that wall divided by the area of that wall. And that area of that wall is of course L times L, so L square. So this divided by L square, you got the L cube at the bottom. And L cube is simply the volume of this cube. What about n times m? N is the number of gas particles and m is the mass of each gas particle. So n times m would be the total mass of this gas. So what we are looking at here is actually mass of the gas divided by the volume of the gas times v square. And mass divided by volume would be the density of the gas. Wow, we have made quite an impressive progress. But of course, that's based on this simplified model. We are aiming for this model actually. So what do we do next? Let's recognize the fact that these molecules have different speeds. So instead of one common v, we're actually dealing with lots of different v's, v1, v2, v3, v4 and so on. So the change in momentum for each collision is different, the force due to each particle is different, and for the total force, we cannot do n times of a common mv square over L. But for this, we just have to do one tiny adjustment. So instead of n times m, a common v square over L, we just do n times of a average v square. So there isn't one single v square, but we can always use an average value of the v squares. So phew, that's quite easy. But are we done yet? Nope, we are not done yet, because in the actual model, the gas particles actually move randomly in all directions. So besides the components in the x direction, the velocity also has a component in, say, the y direction. And of course, it can also have a component in the z direction. So the resultant velocity looks something like this. I'm going to use the letter c to represent the resultant velocity. So what kind of adjustment do we have to make to this formula here? Nothing actually. Because if we are concerned with this wall, we realize that the change in momentum occurs only in the x direction. After colliding, only the x components of velocity flip direction, whereas the Vy and the Vz actually are not affected. So the change in momentum for each collision, the force due to each particle and everything remains the same. We just have to recognize that the V in this formula is not the velocity of the gas particles, is the component of the velocities in the x direction. But still, we'll rather have a formula that's in terms of c rather than v, right? So is there any relationship between c and v? Of course there is. C square is Vx square plus Vy square plus Vz square. What you're looking at is just the Pythagoras theorem in 3 dimensions. So there are a gazillion number of gas particles, each of them with a different C. So you have C1, C2 all the way until Cn. But if you sum them up and divide by n, you get the average of the C square. And the average of the C square should be equal to the average of the Vx square plus the average of the Vy square plus the average of the Vz square. Now I want you to look at these 3 terms here and tell me which of these 3 terms do you think is the largest? I think you realize that all these 3 terms should be the same. Because in the kinetic theory, we assume that all the gas particles are in random motion. It's random. So the motion should be the same in all directions. Which means the average of c square should be 3 times the average of v square. V is the component of the velocity in x or y or z direction. So coming back here, we make the final adjustment. Instead of v square in any particular direction, we write it in terms of c square. So just from a very simple assumption that the gas particles are in random motion, we can actually derive a formula for the pressure of a gas. It depends on the density of the gas and how energetic the gas particles are. Awesome. That's all. Ta-ta.